Hello everyone. So today we are going to talk about linear multi-step method, zero stability and absolute stability. So we can define a linear multi-step method in a general way using this formula here. For instance, let's give an example. If we write the Euler method, it could be a one-step method, right? Then we have that u n plus 1, it's equal, minus un, it's equal k times f of un tn. So in this case, our alpha 0, it's equal minus 1, and our alpha 1 equal 1, and our beta 0 equal 1. Okay? So, and here k is the discrete time step, and an R step method needs starting values u0 until u r minus 1. That's what I said before. In the case of the one-step method, we just need the u0 that for the initial value problem it's given. But if we have two-step methods, so it's a two-step, so then we need u0 and u1. And so usually, so yeah, if it's an initial value problem, the u0 is given. And if it's a two-step method, we would need to calculate the u1 using another approach, another one-step method, okay? So we would have to find a way to calculate the some approximation for these initial values, for these starting values. So if beta r it's equal 0, the method is explicit. So in the case of the forward Euler, so our beta 1, it's a one-step method, our beta 1 equals 0, and therefore it is an explicit method. But in the backward Euler, we have something like this. So it's n plus 1 here and n plus 1 here. So now our beta 0 equals 0 and our beta 1 equal 1, and therefore the backward Euler is an implicit method, okay? And yeah, so if the beta r is different than 0, then the method is implicit. So let's see some examples. So explicit Adams-Bashforth method. So the first step here, one step here, this is, as you can see, this is the forward Euler method. And to step 1, we have this other method here. So let's for this 2-step here, our so here, okay, so our alpha 0 equals 0, alpha 1 equal minus 1, okay, because this term here should be in this side, okay, because in the other side we just have terms on k that are being multiplied by k and depends on the function f. And our alpha 2 equal 1. And our beta 0 equal minus 1 divided by 2, okay? And our beta 1 equal 3 divided by 2. And the beta 2 equals 0. So therefore it is indeed an explicit method. And we have examples of implicit Adams-Moulton methods. This first one here is the trapezoidal method. So we can see here that our alpha 1 equal 1, alpha 0 equal minus 1, beta 0 equal 1 divided by 2, and beta 1 equal 1 divided by 2. Okay? And now we have this other method here. It's a 2-step, and you can write the values for betas and alpha to see if you got the concept of how we can write a linear multi-step method using this notation with alphas and betas. So now we are going to calculate some general formula for the local truncation error for linear multi-step method. So consider this problem here, okay? So it's some initial value problem. So we are going to obtain a general formula for the local truncation error. So the local truncation error, it's calculated when we substitute the exact solution on the method. So just coming back here. So the method is given by this, okay? So now we, let's just see here. So we have it, so it is sum of j equals 0 until r of alpha j u n plus j, it's equal k times beta j, and here we have f of u n plus j at the time t n plus j. But remember that the original problem is given like this, so we can just substitute this term like this by this, and we substitute here the original, the exact solution for our problem. So here it will be u line tn plus j okay. I don't know what's going on. Okay, and here u of tn plus j just minus this, there is a k here. So now this equality that we had before doesn't hold because it just holds for the approximation. And now when we substitute the exact solution, we are having some residual, okay? Which is the difference between which is created by substituting the exact solution on it. So now we are going to do some Taylor expansion here at this term and this term. Okay, so for here first, for u, so we are considering that tn plus j, it's tn plus j times k, where k is the time step. So we are doing some Taylor expansion around the point tn, okay? So we have this first here on u, and we do the same on the function u line, okay? Also around tn. And then we substitute it at the local truncation formula, and we substitute this here. So we substitute here and here. It's missing some parentheses here. And if we just write it in terms of these functions here, so we are just putting on evidence the terms that are multiplying these functions. Then we say that the method is consistent if the local truncation error goes to 0 as k goes to 0. So we have seen this on the last class. So so we have here this, we got this equation for the local truncation error. And if we do k go to 0, we see that this term here will go to 0. And this term here will go to infinite, right? So because if k go to 0, then 1 divided by k go to infinite. So for having this going to 0 as k go to 0, this term here should be 0, okay? And then we won't have the influence of this term here. And also, we want this term here to go to 0, okay? Because here it's some constant, so it doesn't depend on k. It means that if k goes to 0, nothing happens to this term. It will still be there. So this term here goes to 0, and here it's plus terms of the order of k squared, which goes to 0 as k go to 0. So we want this term here to be 0, okay? So for that, so this equals 0, and then this should happen, and for this term here to be 0, this should happen, okay? So we can define some characteristic polynomials for the linear multistep method, and then we can define the consistency looking for the conditions on these polynomials, okay? So the consistency, remember, is that the local truncation goes to 0 as k go to 0. And remember that the conditions that we got before, it happens when the sum of alpha j, for j from 0 until r, it's equal 0. So this is the first condition. So if we define some polynomial whole on Kc, so this, I think it's, no, Kc is this one, right? I don't remember the name of this letter. I will call it Kc, okay, if it's all right. So if we define some polynomial on Kc, so this polynomial at 1, it will be the sum of alpha j, which is equivalent to this. So we require that this polynomial whole to be 0 at for c equal 1. And the second condition was this one, okay? So we want that, I'm just getting some space. So we want that the sum of j times alpha j for j going to 0 until r, it should be equal to the sum of beta j equals 0 until r. And we just notice that if the whole equal this here, so whole line of this letter C, it will be j times alpha j times the Kc of j minus 1, for j going to 0 until r. It could also be j going to 1 because then it doesn't matter. Ah, okay, I wrote it here, okay. So for whole line of 1, it will be equal the sum of j equals 0 until r of j times alpha j. And now let's look for this polynomial here. For sigma of 1, it will be beta j for j equals 0 until r. So if we require this to be equal this, we are actually trying to to satisfy this condition. Okay? Let's see some example now. So consider the two-step Adams-Moulton method that's given by this, and let's just write the characteristic polynomial. So for writing the characteristic polynomial, we need to have a look and pay attention on its coefficients. So first we write alpha 0 equals 0, because the alpha 0 is the term multiplying un, okay? And so if we put this term on the other side, we see that alpha 1 equal minus 1, and alpha 2 equal 1. And therefore, if we write the polynomial like it is, would be 1 times, so it's alpha 2 times psi to the second, alpha 1 psi to the first, plus alpha 0 psi to the 0, which is 1. Okay, so then we get this in fact, and let's look for the beta. So beta 0 equal minus 1 divided by 12, beta 1 it's equal 8 divided by 12, and beta 2 equal 5 divided by 12. So looking at that conditions that we have seen before, so for the method to be consistent, remember, consistent means that the local truncation error goes to 0, sk go to 0, okay? We are going to see soon why it's important for the method to be consistent, okay? Because, yeah, so we are going to talk about this later. So for the method to be consistent, as we saw before, we require that rho of 1 equal 0, and that whole line of 1 equal sigma of 1. So the whole of 1 equal 0, so the first condition is satisfied, and we calculate a whole line equal 1, and this equal 1. So we have that this second condition is satisfied, and then we say that this method is consistent,